So, hello all. This is Dr. Deepesh Kumar Jain. I'm working as a scientist D in the Monsoon Mission Group at Indian Institute of Tropical Meteorology. Uh, Indian Institute of Tropical Meteorology, we basically do basic research on weather prediction, monsoon predictions per se. And a little bit introduction about myself. I did my master's and PhD in climate science from Indian Institute of Science, Bangalore. Then I have been working here at IITM since last 6 years, actually 8 years, and I'm responsible for developing the next generation of weather prediction models here. So AI plays a very big role nowadays. What I'll do is I'll discuss briefly, or not briefly, actually in detail, so that you appreciate what we are trying to accomplish here. The conventional way of making weather predictions, and then you can appreciate where the AI and ML algorithms basically help us. Okay, so this is currently our building, the Indian Institute of Tropical Meteorology, and we are basically the Monsoon Mission Group is focused on the seasonal forecast of monsoon. So when I say seasonal, we are looking at June, July, August, September rainfall, which is very crucial for the Indian farmers. Okay. So I'll give you a detailed view of how we do weather prediction. So if you look, see, you can't make a weather prediction just locally. What is happening around the globe affects what happens over Indian region. Everything in atmosphere and ocean is connected. So the way you do it is basically you write three conservation laws of basically, so mass is conserved, momentum, that is u and v, wind velocities are conserved, the energy is also conserved over Earth's surface. So basically divide the entire Earth into graded structure, horizontally and vertically, and you solve the equations for u wind, v wind velocities, and then energy and mass. So if you basically look at the grid, you have on your left uh, corner, you can see the grid which basically has all the processes that are going on. So you have ocean interacting with atmosphere, and the radiation is also coming in, and some of it is blocked by clouds, and some of it makes way all the way through to land. So when you are solving these equations in space and time, that's when you basically are able to uh, make a prediction. Now, if you want to understand the limitations, you just take one of the grades. Okay. Now, the only information that we have is at the grid edges. So at these grid endpoints. Okay. At any given time, what you get is a graded data. Based on that graded data, you are trying to predict what is happening inside. So these small cloud processes, suppose if you look at the entire cloud structure, this is interacting with the surface. There's a mixing happening. There's all sorts of clouds in between, and then there is descent and updrafts happening, right? So all these processes are interacting with each other, and you are not able to resolve it because your model grid sits at the corners. So you're trying to make a prediction of what is happening inside the grid box based on what is available to you. So this entire process of writing the equations, so these are basically physically based equations, physics based equations. And what you're trying to do is make a prediction on how to parameterize these processes. And that's where the inherent limitation comes. Okay. So if this was just an example of cloud, and if you now look at all the processes that are happening, so cloud is only one process. You have boundary layer. So boundary layer is just 500 meters above the surface. That behaves very differently from compared to clouds. And then you have hydrological processes. When I say hydrological processes, you have rivers and you have oceans and all these things. Then you have radiation and chemical processes, and ocean and land surface processes as well. So you can understand the gigantic problem that we are trying to solve here with the nonlinearity coming into picture, right? So to solve these, you have a very big code base, something like what we have had since. So we are continuously developing models, right? So each process is a separate model. You can say that if I put together the entire code for solving these equations, I can have atmospheric model, I can have land model, I can have ice model, and I need to couple these together with ocean model, right? Now the problem is once you write a code that is lakhs and lakhs lines of code, and if you wanted to change something, then change something substantially, then the legacy nature of the code becomes a problem, right? So in the newer version of the model, what we have done is on your left, you have the older version of the model, which is still used by IMD to make predictions. And on the right, we have developed the new system, which is now making predictions. So we have made it like a software where you basically have standards on how to basically interact. Now, again, the inherent problem lies still with the predictability that I'll show you. So even after upgrading all the model components based on physics and everything, uh, I'll not go into details, but just know that this table refers to all the upgrades that we made to the older model, just physics based, so that we get a better prediction. And here down, you see the grid sizes that we are dealing with. So Earth is divided into, in the old model, it was divided into 1152 by 576 grid points and 64 levels in the vertical. Now, in the ocean models, at least we are dealing with 1440 into 1880. I'll come back to this number when I'm talking about the computational requirement that is needed to run these models. Okay. These are the experimental details that we ran. So any model that you develop basically has to be verified. So these models are not only run for Indian nation. So if you see, I have shown the entire globe, basically the tropical region. And when I say GPCP, GPCP is satellite based observations. So your model should match what is observed. So the older version matches with observations. You can see a lot of rainfall. So this region is Bay of Bengal. You can see a lot of rainfall over Bay of Bengal, which is also seen in observations. The model is able to simulate it, but then the model is like kind of over predicting the rainfall, how much we can get. MMCFSP2, that is a newer version of the model, is kind of very near to observations. On the left, on the right side, I'm showing you the differences from observations. You can see over Indian region, our both the models. So blue region basically says I was under predicting the rainfall. Okay. So both the models still suffer from a problem of under predicting. But if you look at the skill of the model in capturing the sign of rainfall over Indian region, we have improved the predictability from 0.55 before. So if you take the average of rainfall over the entire Indian region, and you plotted the time series and you calculated the correlation, the previous model was capturing at a correlation of 0.55. Now we have been able to improve it to 0.72, which is a substantial improvement. So just based on physics, we have been able to improve it. Okay. Mhm. Based on the other matrix also, like your normalized root mean square error or root mean square error, we are getting the best model that we have currently right now. So this is going to be operational model for IMD in the near future with a scale of 0.72. Now, compared to globally, what how we are doing is we have compared this our model with GFDL. So GFDL is US based model, and it is getting a correlation of 0.61, whereas we are getting a correlation of 0.71 and 72. Uh, okay. Even in terms of whether we are able to get false alarm rays or excess or droughts or normal years, so it's very important that we get the normal years correctly or the excess or drought years correctly. And even in that terms, Our new model is able to capture it very well. So now you can understand, just based on physics, this is like 10 years of development right here, just based on physics. So we have kind of reached, and the potential predictability for a dynamical model is like 0.79. We have already reached a potential like the predictability of 0.72. So we are very near the potential predictability. If you look at the uh, nonlinear theory of chaos, basically it says you can't make prediction beyond certain days, just based on the errors in the initial conditions. So we are very near the potential predictability limits here. Now, what is the way forward is use of AI ML. I'll also show that the predictability just over Indian region is not a localized phenomenon. So when I say Nino 3.4, Nino 3.4 refers to the SST over the Pacific Ocean. This is a certain region of Nino 3.4. And the SST anomaly is basically when you subtract the climatology, that is affecting our Indian regions. When in the news they say this was an El Nino year and you are going to get less rainfall, you can see that here. So when there's a blue region over Indian region, so what it says is when there is a positive El Nino, you have a negative rainfall, right? And this is how the Indian rainfall is affected by SSTs globally. So you can see that how much of Indian rainfall is affected by global signatures. It's not just local phenomena. So when we are developing AML techniques, we most of the people think that okay, we need to basically focus on the Indian region data, but that's not the case. I'll show you the results where we have trained the model for Indian region and globally, and where the predictability limits come. Right. So Indian monsoon is truly a global phenomenon. It's not local. Okay. This is even being a global phenomenon for like for farmers per se. What is really important is how am I going to get a rainfall in my particular region. Now, as a scientist, I can say that okay, fine. This is a global phenomena, and until and unless we are able to get the global signatures right, uh, getting local signatures right is difficult. Here I'm showing the local signatures with the newer model, and you can compare it with like we were getting 0.09 for central northeast region, whereas the newer model is getting much better results. Okay. Now, suppose you wanted to run a local model at a very high resolution. So I am showing here an example of a WRF model which was set up for a very high resolution of 3 kilometers. You can understand 3 kilometer running, the uh, number of grid points that you're dealing with just over Indian region is 1000 by 1000 and 64 in the vertical. So if you talk in terms of number of calculations that are done, that is 64 million calculations per variable. So you have 128 variables, 64 into 128 million calculations per time step just to make this prediction. Right. And what is more important for us is, see, I come from a place called Nagpur, right? Nagpur is cotton based agriculture, and cotton is very largely affected by the variations in rainfall. It doesn't need much rainfall. And uh, see, there were 11,000 suicides in Nagpur in 2022 just because the agriculture yield was not that great. Now, if we can make the predictions of the rainfalls correct regionally, that number should go down. That is very important. I'll give you an example of why a high resolution model, even with the right physics, is very important. So this is an example of southward propagations, which is very big signature of Indian summer monsoon. This is only captured when you have a very particular set of physics. If you change the physics, you stop getting the signature. So the models, right now the models are very sensitive to physics that you choose. Okay. So the biggest problem is if I wanted to go local prediction, but taking into account the global signatures, So I need to run a global model at a very high resolution. I can't run a local model with a very high resolution and expect the predictability to be very high. Now, if I go to 1 kilometer resolution, let me just tell you what we operationally do. So operationally, we are running 1152 grid points in the x direction, 576 in the y direction, and the computational requirement is 1 petaflops for the supercomputer. And each of the simulation that we do for monsoon takes 8 terabytes of space. Now, if I wanted to go to 1 kilometer or 3 kilometers, let's say 1 kilometer, I'm talking in terms of 40,000 grid points in the x direction, 20,000 grid points in the y direction. And since the resolution is increased, I also need to increase the resolution in the z direction, and I need to decrease the time step of the model. So each simulation will be, it is 6.4 petabytes. Now you can imagine the mammoth of a problem that we are dealing with, and here is where the AI comes into picture. So we recently have had a very high performance computer that is the highest in India. This is 11 petaflops, and it is one of the top 500 computers we have submitted to. Now the limitations is, first of all, for solving a dynamical model, you have to assimilate all the information that is available. You have information from satellites globally, and you have information from ground-based and ship-based. And see, if one person was supposed to do all this data assimilation, it becomes a very big problem. So assimilating all this information, we need to automate it. We need to automate the uh, outlier basically filtering, and we need to basically do near real-time data assimilation. Okay, and the sources of information is very uh, disparate. So you have data from mobile phones, wireless sensor networks. So this is one of the biggest problems where AI/ML should be used, and we have already started basically developing products and techniques to automate this process, but there's a lot to be done. Okay. The other problem is, as I told you, the resolution. Once we increase the resolution, so right now we are running for short-term predictability, like 3 days predictability, we are running at 12 kilometer resolution. For seasonal, we are running at 35 kilometer resolution. Now, if you wanted to go higher resolution, the model simulation itself takes like 1 month. At 1 kilometer resolution, it'll take 1 month to simulate what is happening in 1 month. So practically, that becomes kind of useless if that time window is already passed. So most of these physics that is happening in the model, we need to develop emulators for them, which can basically solve physical parameterizations within seconds rather than within minutes or hours for each time step. So this is one. And as I told you, like this, the computational requirement itself is compared to the current one, that is almost 2.4 million times more. So the way forward is improving process understanding and their parameterization is based on artificial intelligence and machine learning. Dynamical core is basically the way we solve or integrate these equations in time and space. So if we can accelerate those using AI/ML, that is also great. Increasing the resolution, as I already told you. So, but there are different ways of increasing the resolution. So if you use conventional way of using kind of a dynamical model called WRF or some other model, this is very time consuming, very computationally expensive. So I'll show you a few of the works that we have done in downscaling using machine learning. We should also be using AI/ML to basically filter out all the improper data, missing data, outliers, and detecting basically malfunctioning sensors. Data assimilation is another one, as I showed you the past figure, where we were assimilating all the data that was available. We need to automate these processes to assimilate the data. So to address these problems, the Ministry of Earth Sciences, under which IITM and HCMRWF and 7 other institutes come. They established a virtual center for AIML in 2021. The responsibilities were to basically explore areas of AIML in climate and weather prediction, to basically establish multidisciplinary programs in the field of earth sciences. And we have been conducting workshops and hands-on sessions and training sessions for MOS scientists so that they are equipped with using AIML in weather prediction applications. So these are, when I say research work done so far, this is just a brief introduction as to the research works that we have already done. So we are already producing 1 degree short range weather forecast using AIML. We have tested many algorithms for scaling precipitation data. We have made a system for fire location forecasting, for fog forecasting, lightning and thunder. And we have been exploring deep learning for improved global precipitation. So most of the models that you see being developed by Google or like NVIDIA, they don't focus on precipitation directly. The variables that they focus primarily is winds and temperatures, because those are the easiest one to forecast. We at IITM are focusing on using deep learning to basically predict precipitation, because that is very important for Indian region. Okay, so this is just an example of deep cloud sort of AI. So if you want to understand process levels, you are basically have to explicitly simulate these processes. So cloud, you cannot just say, okay, very limited data available, I'll just write some equations and that is it. What we do here is we explicitly three-dimensional data, direct numerical simulations we do at 1 mm resolution, and those are very computationally expensive. So like 60-hour simulation of on a cube of 60 centimeter by 60 centimeter took us a month to finish, right? So then we developed a technique called deep cloud.ai, which basically replicated what was happening in a direct numerical simulation over to a very big domain. Flashbench is a lightning nowcasting framework based on hybrid deep learning and physics-based analytical models, which inherently uses convolutional LSTM. Uh, I'll briefly show you how we are using deep learning for improved global precipitation and numerical weather prediction model, and fire burning locations as well as downscaling. So let's start with deep learning for improved global precipitation. As I told you, most of the models, current models, do not focus on precipitation directly. We focused on precipitation. We used UNet architecture based on deep convolutional neural network with residual learning, and we took input variables as total cloud cover, to 2 meter air temperature, and total incident solar radiation to simulate three different cases. On your right, you can see basically the top one is our conventional model, numerical weather prediction model. And if you see, basically I'm showing the correlation coefficient. And if you can see DL1 and DL2, when we are using total cloud cover and 2 meter air temperature, the correlations are very, very high. Okay. But total incident solar radiation is not very high. So the question becomes, it's not just like throwing in all the data to the deep learning algorithm and okay, saying fine, we'll make a prediction. The scientific problem here is to choose the variables correctly. So if you can choose the variables correctly, you can get a very high accuracy. Okay. The second paper that I'm showing is basically deep learning for fire burning locations. We focused on two regions here. First is Delhi, Punjab. So the deep learning model was able to get these locations correctly for at least Delhi, Punjab region. For Northeast is a very different region. You have the Himalayan region playing all sorts of things, and uh, giving the input data to the deep learning model becomes very problematic. See, one of the variables is the geopotential height, and geopotential height is affected by a lot by the orography there. So the predictability is not that great over the northeast Indian region. So again, coming back to the problem of what variables to give where. So it is not just giving all the variables as input and expecting the same results. It also depends on the location as well. Uh, this is here I'm showing the deep learning for downscaling. Downscaling is the process of increasing the resolution. So if suppose your dynamical model predicted at a resolution of say 25 kilometers and you wanted much finer details, you can either run a model like WRF dynamical model at a resolution of 12.5 kilometers or 6 kilometers. That can also give you downscaling, but that has a cost of computation that requires a lot of computation. Or otherwise, you can basically teach a deep learning algorithm which does it for you. So here we are, I'm showing you various algorithms that, so SR, super resolution generative GAN, and UNet and convolutional LSTM and deep SD. You can see that SR-GAN is basically predicting much higher correlation coefficients. Okay, so we here at IITM are testing all sorts of algorithms for basically making predictions better. Uh, Now we also have models which are completely neural network based. Okay, the biggest problem or the biggest gripe I have with these complete AI models is they are trained based on reanalysis data sets. Now, reanalysis is nothing but observations combined with model simulations. When I say model simulations, the dynamical model simulations. As we have already seen in the previous slides, a dynamical model might not be giving you all the correct simulations. Now, if you basically trained your neural network model based on ERA, those limitations will also come into your model. But that's the best that we can do right now. As we increase the number of observations over Indian region, that result should become better. Here I am showing you the two models. ForecastNet is by NVIDIA, GraphCast is by Google. So for ForecastNet, we retrained the model just over Indian region. They had also ForecastNet is also available for globally trained data. GraphCast was already trained for global data. We did not train it for Indian region. And these are the details. The training was done from 1940 to 2015. Validation for 2 years, 16 and 17, and testing was 2018. So the results I'm showing is 2018. Uh, if you look at the regions over Indian regions, so we call them as homogeneous regions because the rainfall over these regions is kind of homogeneous in nature. And if I compare the precipitation directly, you can see that ForecastNet Global, which is this one, the blue one, and compared to the pink one, the observations, the ForecastNet Global has significant negative bias for all days. But when you are training only over Indian region, you get substantially reduced bias. So bias, when I say bias is the difference between what is observed and what is simulated. The bias also depends on the days of forecast. So whether you are making 1 day forecast or 3 days forecast or 5 days forecast or 7 days forecast, the accuracy changes. So if I come here, here I'm showing the root mean square error and the correlation. So ForecastNet Indian has lesser root mean square error compared to ForecastNet Global for all regions and all days almost. But when you are talking about day 7 forecast, it is kind of very near to, so where your global signatures like El Nino or IOD becomes important for local predictions as well. Um, Graphcast has one of the lowest RMSCs and one of the best correlation coefficients. So the reason I speculate for this is GraphCast is being trained on 10 vertical levels, whereas ForecastNet Global is trained only over uh, 5 vertical levels. As we increase the number of vertical levels for our ForecastNet, the accuracy should improve. Uh, the other kind of problems that we are targeting here at IITM is we are trying to use deep learning very deep into the physical physics of the numerical weather prediction model. So one of the biggest problems with numerical weather prediction model is the cumulus parameterization. This is an article published by Siddharth, one of my colleagues. He has developed. So basically, what the biggest problem with conventional numerical models is they trigger a lot of precipitation quite frequently. So he came up with a new trigger based on uh, machine learning. He basically took all the variables depending on their significance on the rainfall, and he basically did SVM and machine learning, deep learning. So when I say cape and decape, these are basically referring to the conventional way of triggering the convection, right? And SVM. So here I am showing you number of events. False. So TN is total number, false positives, false negatives, and TP. So if you just like let's say we are looking at moderate rainfall. So true negatives, if you can get right to true negatives, that's better. Okay. So for a neural network, you are basically getting the highest number of true negatives and you are getting the least number of false positives. But if you compare it with the conventional way of triggering the convection, you can see that false positives are much higher and true negatives are much lower. And this is true for all the cases that we have observed. So weak convection or moderate convection, high convection. Okay, so here are my 2 cents. Basically, this is the last slide. We need to work a lot on basically using AI/ML for discovering weather patterns and using them to basically improve our understanding, physical understanding of the process. We need to automate the data flow and accelerate data management in weather prediction. There are a lot of solutions that are being coming up for disaster management. We review a lot of such proposals, and we would like to combine AIML with agricultural advisory. So the biggest problem, one of the biggest problems, is getting the information to basically the farmers. That's about it. Yeah. Thank you. Questions?
Yes, sir. We have a few questions from our side. I had 3 or 4 questions, so you
Okay.
can. I'll tell them to you one by one, and you can answer them, sir.
Okay.
Okay, sir. So the first question is, what is the hardest part of in the database aspect of your job, sir?
So the hardest part is the size of the data itself. See, I told you, right? We are running at 6 kilometer resolution. My 35 kilometer resolution, one simulation is 2.3 terabytes. And now we are basically running. So, if you know anything about non-linearity aspect of uh, weather flow, you need to run ensembles. So we are running 10 ensembles for each forecast. So that is 23 terabytes of data, right? Making this prediction in time and providing it to the stakeholders, that's the biggest challenge.
Yes, sir. Another question that we have received is, what are the hardware in terms of the computational aspects that you use? What is the hardware in that?
So right now, see, most of the codes is a legacy Fortran code. The reason to use Fortran is not just the legacy code, but the fastest rate at which it can solve array to array operations. Now, if you look at the weather data, it is array data mostly. Now, what we use is a lot of CPUs right now to basically solve over the entire grids. Now we are also exploring with industry partners how we can accelerate most of the code using GPUs. But that is a research problem here.
Okay, sir. The last question that we have received is everything that you use custom built or did you purchase it from a vendor?
So, see, most of these codes, since they're written by scientists, they are open source. You can probably download it and run it.
No,
The
no, sir.
problem,
Actually, they didn't mean the codes. They meant the hardware that you use. Is it custom built or have you sourced it
yeah,
externally?
the hardware is custom built for the institute based on the kind of problems that we are trying to solve. We give them the specifications. Basically, there's a very lengthy process, very involved process. We get HPC after like 7 years. When see, yeah, I mean, this is a very lengthy process, which is of getting hardware.
Yes, sir. Those were all the questions that we have received. You've explained it very well. I think that's why there are not many questions related to the basic aspect. So
I
we would
hope
like
so. Yeah.
Yes, sir. So we would like to thank you for taking out your valuable time to attend this session. And it's a very good topic that we were honored to have presented over here, as this is a topic that people don't know much about, even though it affects a majority of their lives, how they plan their day, how maybe they would adjust their day by day schedule if the weather isn't right. And you play a very
Correct.
important part in that, sir. So once again, thank you very much, sir, for attending this, for hosting this session for us. And we wish we can do many such sessions like these again to enlighten the students, sir. Thank you, sir.
Thank you. Thanks a lot.